this episode, we're going to take the mystery out of the numbers and targets that make control systems feel alive, because beginners often hear terms like process variable and set point and assume they are just fancy labels for data. In OT, those values are the language a physical process uses to communicate what is happening right now and what it is supposed to be doing. When a control loop is calm, it can feel like the system is simply holding things steady, but under stress the same loop can wobble, overshoot, lag, or even chase the wrong goal if something is misread. That behavior is not random, and learning to recognize it is one of the easiest ways to understand both safety risk and security risk in industrial environments. You do not need to do advanced math to follow this, but you do need a clear mental picture of how measurement, targets, and adjustments interact. Once you have that picture, a lot of OT scenarios stop feeling like black magic and start feeling like predictable cause and effect. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A process variable is the measured value that represents the current state of something important in the physical process, and it is often the primary input a control loop uses to decide what to do next. The most common process variables are things like temperature, pressure, flow, level, speed, and concentration, but the deeper idea is that a process variable is a stand-in for reality. The controller does not feel heat or pressure directly, so it relies on a sensor to provide a number, and it treats that number as the best available truth. That is why the quality of the measurement matters as much as the logic that uses it, because a perfect controller cannot make good decisions from a bad signal. Beginners sometimes think a process variable is just a reading on a screen, but in a loop it becomes the feedback that tells the controller whether it is winning or losing. When you understand that feedback is constant and continuous, you can see why problems like sensor drift, noise, or delay can create stress even when nothing is broken in the obvious sense. In OT, a stress measurement is often the first hint that something else in the process is changing. A set point is the target value the control system is trying to maintain for a process variable, and it acts like a goal that guides every adjustment the loop makes. If the process variable is what is happening, the set point is what should be happening, and the difference between them is what drives corrective action. That difference is often called error, not because someone made a mistake, but because it quantifies how far the process is from the target. Beginners sometimes assume set points are fixed, but in real operations set points can change based on production needs, safety constraints, time of day, or process phase. A set point change is not just a new number. It is a new instruction to the loop, and the loop will respond by moving the process toward that new target. How it moves depends on the system design, the controller settings, and the limits of the physical equipment. When set points are changed too aggressively or without understanding process dynamics, the loop can become stressed because it is being asked to move faster than the process can safely move. Understanding set points helps you see why change control and authorization matter in OT, because a set point can be a lever that shifts real-world behavior. A control loop is the repeating cycle where the system measures the process variable, compares it to the set point, and then adjusts an output that influences the process. That output might be a valve position, a motor speed command, a heater power level, or another actuator-driven signal that changes the physical world. The loop repeats because the physical world is never perfectly steady, and even small disturbances can push the process variable away from the set point. In a stable loop, the controller's adjustments counter those disturbances, keeping the process within an acceptable band rather than at a mathematically perfect value. Beginners often imagine the loop as a single action, like turning something up or down, but it is better to imagine it as a steady conversation between the process and the controller. The process responds to the controller observes the response, and then the controller adjusts again, over and over. This is why timing matters, because if the controller reacts too slowly, it may fall behind, and if it reacts too aggressively, it may overcorrect. Under stress, the loop's behavior is basically the story of how well that conversation is going. One reason control loops behave differently under stress is that physical processes have inertia, delays, and limits that do not exist in purely digital systems. If you heat a tank, the temperature does not change instantly, and if you change a valve position, flow may respond with a lag depending on system pressure and equipment characteristics. This means the controller is often making decisions based on measurements that reflect the past, even if only by seconds, and in fast systems, even fractions of a second can matter. Another reality is that actuators cannot do infinite work, so they may reach maximum or minimum positions, and when they hit those limits, the controller loses some ability to correct the process. Stress can also come from external conditions, like a sudden change in demand, a supply fluctuation, or a mechanical issue that changes how the process responds. Beginners sometimes think stress is always a dramatic failure, but it can be a normal event like starting a pump, switching a batch phase, or a large load turning on. The key is that stress reveals the underlying dynamics of the loop, showing whether it is tuned and designed to handle change gracefully. When you learn to recognize those dynamics, you start seeing OT systems as predictable systems, not mysterious ones. A helpful way to understand loop behavior is to think in terms of proportional response, which is the idea that the loop reacts based on how far the process variable is from the set point. When the error is small, the adjustment is small, and when the error is large, the adjustment is larger, which feels intuitive because bigger problems get bigger corrections. Many control approaches also include accumulation over time, which means if the process variable stays below the set point for a while, the controller increases its corrective effort because it has learned that the small correction was not enough. This is one reason proportional integral derivative, PID, control is commonly discussed, because it combines a response to current error, a response to error over time, and a response to how quickly the error is changing. You do not need to calculate these terms, but you should understand what they represent in plain language. Under stress, a loop might show overshoot if it corrects too aggressively, or it might show sluggishness if it corrects too gently. If the loop starts to oscillate, that can be a sign the corrections are arriving too late or are too strong relative to the process dynamics. Recognizing these patterns helps you interpret alarms, trends, and operator concerns in OT scenarios. Set point changes are a special kind of stress because they can be intentional, frequent, and sometimes poorly planned. When a set point jumps from one value to another, the loop sees an immediate error and responds as if a disturbance occurred, even though the change was commanded. A well-managed system often limits how quickly a set point can move, or it uses a ramp so the target changes gradually, which reduces shock to the loop and to the equipment. Beginners sometimes expect the system to move directly to the new target like a thermostat in a small room, but industrial processes can have large volumes, high energies, and safety constraints, so fast changes can create unstable behavior or unsafe conditions. Another risk is that a set point change can interact with equipment limits, like asking for more flow than the pump can provide, which leads to saturation and poor control. When saturation happens, the controller may keep demanding more because it cannot see that the actuator is already at its limit, and that can create a sense of stubbornness in the loop. This is where good design includes awareness of constraints, and good operations includes choosing set points that the system can realistically achieve. In security terms, unauthorized or accidental set point changes are risky because they can stress the process without leaving obvious signs of malware, yet the impact can still be real. Disturbances are another major source of stress, and they are simply changes in the process that push the process variable away from the set point without the operator deliberately changing the target. A disturbance might be a valve upstream changing position, a raw material quality change, an ambient temperature shift, a sudden demand spike, or a piece of equipment wearing out. Good control loops are designed to reject disturbances, meaning they detect the change and adjust outputs to bring the process variable back toward the target. However, disturbance rejection depends on the loop having timely and accurate feedback, and it depends on the actuator having enough authority to counter the change. Beginners often assume the controller is always the main actor, but disturbances are often the real reason the controller has to work hard. In a trend view, disturbances can show up as a sudden dip or spike in the process variable, followed by recovery that might be smooth or might oscillate. Under heavier stress, recovery might take longer or fail altogether if the process cannot return to target due to a constraint. Understanding disturbances matters because many OT incidents, including security incidents, can look like disturbances at first, and the ability to separate normal disturbance behavior from abnormal manipulation is part of good judgment. Measurement problems can create loop stress even when the physical process is behaving normally, which is why sensor quality is such a critical theme in OT. Noise is one common issue, where the measured process variable jumps around due to electrical interference, vibration, poor wiring, or sensor limitations. If the controller treats that noise as real change, it may chase the noise, causing unnecessary actuator movement that wears equipment and creates instability. Another issue is drift, where the sensor slowly becomes biased over time, causing the measured value to differ from reality and leading the controller to make corrections that are consistently off. Delay is another challenge, where the measurement arrives late, meaning the controller responds to old information, which can cause overshoot and oscillation. Beginners sometimes think that since a number is displayed, it must be accurate, but OT teaches you that a number can be wrong in subtle ways. Under stress, these subtle measurement issues become more visible because the loop is already working hard and small errors have larger effects. From a security standpoint, measurement integrity is a key concern because if an attacker can influence what the controller believes, they can influence how it acts without directly touching the actuator commands. In other words, a stressed loop might be reacting perfectly to bad information, which is still a dangerous outcome. Actuator behavior is the other half of the stress story, because even a perfect measurement and a perfect controller cannot achieve stability if the actuator cannot respond as expected. Actuators can have deadband, which means small command changes do not produce movement, causing the controller to keep adjusting until the command is large enough to overcome friction or mechanical slack. Actuators can also be slow, sticking, or underpowered, making the process respond more slowly than the controller expects. Saturation is especially important because when an actuator hits a limit, like a valve fully open, the loop loses its ability to correct further in that direction. Under stress, this can lead to sustained error, and if the controller accumulates corrective effort over time, it can build up a large demand that cannot be satisfied. When conditions later change and the actuator is no longer saturated, that built-up demand can cause an overshoot, making the process swing past the set point and creating oscillation. Beginners may interpret this as the system suddenly going crazy, but it is often a predictable result of limits and accumulated correction. This is why OT teams care about actuator health, maintenance, and proper sizing, because control quality is not only a software question. In security scenarios, actuator manipulation or disablement can create stress patterns that look like equipment failure, which complicates detection and response. Process dynamics add another layer, because different processes respond to control actions in different ways, and that influences how stress shows up. Some processes respond quickly, like flow changes in certain piping, while others respond slowly, like large thermal systems or large tanks. Some processes have coupling, where changing one variable affects others, like adjusting steam flow affecting both temperature and pressure. Some processes have nonlinear behavior, where a change has a small effect in one range and a large effect in another range, making control harder under certain conditions. Beginners often assume the controller always has a simple, straight relationship between command and result, but many real processes are messy, and control is about managing that mess. Under stress, you might see a loop that is stable at one operating point become unstable at another because the underlying dynamics changed. That can happen when equipment degrades, when operating modes shift, or when production requirements change. This is also why simulation and testing are valuable, because they help teams understand how the loop behaves beyond normal steady conditions. In exam scenarios, recognizing that processes have dynamics and limits helps you avoid choosing answers that assume the world is simple and immediate. A mature understanding respects that the loop is managing physics, not just numbers. Operator interaction can reduce stress or amplify it, and beginners should understand that humans are part of the control loop environment even when the controller is in automatic mode. Operators may switch a loop to manual control during troubleshooting, meaning the operator directly adjusts the output rather than letting the controller do it. Manual control can be a stabilizing move if the controller is misbehaving, but it can also introduce risk if the operator does not have good visibility or if the process changes quickly. Operators may also adjust set points, limits, or alarm thresholds, and those choices can either keep the loop within safe boundaries or push it toward instability. Another aspect of operator interaction is alarm response, because frequent alarms during stress can create distraction, and distraction can lead to rush changes that worsen the situation. A well-designed environment supports operators with clear displays and meaningful alarms rather than noise, because clarity helps humans make steady decisions. In security terms, compromised displays or misleading trends can lead operators to make incorrect manual adjustments, which means manipulation of visibility can become manipulation of action. This is why HMI integrity and historian integrity matter, because the operator's mental model is built from what they see. Stress is often when that mental model is tested, and good systems help the operator see the truth. A particularly important stress pattern to recognize is oscillation, because it is both common and misunderstood by beginners. Oscillation is when the process variable repeatedly swings above and below the set point, often in a rhythmic pattern, instead of settling smoothly. This can happen when the controller is tuned too aggressively, when measurement delay is significant, when the process responds slowly, or when actuator deadband and saturation create lag and overshoot. Oscillation can also be triggered by frequent set point changes or by an external disturbance that keeps repeating, like a fluctuating supply. The danger of oscillation is not just that it looks messy, but that it can wear equipment, reduce product quality, and in some cases create unsafe conditions if the swings cross critical limits. Beginners sometimes think the solution is always to tighten control so it reacts faster, but reacting faster can make oscillation worse if the loop is already overcorrecting. Stability often requires a balanced response that respects process inertia and measurement delay, even if that means accepting a slower return to the set point. This is a useful lesson for security thinking as well, because aggressive responses can sometimes create more harm than the original problem. Recognizing oscillation as a symptom of feedback behavior helps you reason about what kind of issue is likely, even without detailed tuning knowledge. When you connect all of this to security OT plus style scenarios, a clear theme emerges. Stress reveals whether the system's feedback, targets, and limits are being managed responsibly. A stress loop can be a normal operational event, like a load change, or it can be a sign of equipment issues, like a sticking valve or a drifting sensor. It can also be a sign of malicious manipulation, such as altered sensor signals, unauthorized set point changes, or logic changes that tweak how the controller responds. The exam does not require you to diagnose like a senior engineer, but it does expect you to understand what kinds of factors can produce certain behaviors. If a process variable is noisy while the physical process appears stable, measurement issues should be on your radar. If the controller output is pinned at a maximum and the process variable cannot reach the set point, actuator limits or process constraints should be considered. If the process variable behaves normally until a particular mode or set point change, process dynamics and sequencing should be considered. In all cases, the beginner skill is to think in terms of cause and effect rather than treating alarms as random. That mindset supports safer decisions, better communication with OT teams, and more accurate interpretation of what is being asked in questions. To close, mastering process variables and set points is really about mastering the basic conversation between the physical world and the control system, because control loops live on feedback and targets. The process variable is the measured reality the system believes, the set point is the desired reality the system pursues, and the control loop is the repeated cycle that tries to close the gap between them. Under stress, that cycle reveals its strengths and weaknesses through patterns like sluggishness, overshoot, saturation, noise chasing, and oscillation. Those patterns can come from disturbances, measurement problems, actuator limits, process dynamics, and human interaction, and understanding each category helps you reason through OT scenarios without guesswork. This also connects directly to security because the integrity of measurements, the authorization of set points, and the protection of logic determine whether the loop is responding to truth or to manipulation. When you can describe how a loop should behave and how it tends to behave under stress, you gain a practical lens for interpreting alarms, trends, and operational constraints. That lens will continue to matter as we move into more detailed OT concepts, because almost every security decision in OT eventually touches the question of whether the process stays stable and safe.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.